Okay, so we're going to move on to week 7, and one thing that I really do want to emphasize at the risk of sounding ranty is use the forum. That's what it is. It's an online course. If there are 2 problems, there should be 2 threads, one for problem 1, one for problem 2. And I'm just going to go back and see how well we did. So if I go to week 6, well, I have 7 posts that I have not looked at. So there's, yeah. So I guess here's one issue, is that Orem should have used this, right? Because so Zach posted the original problem 1 post. This post belongs in here. Shauna then kicked it off with a problem 2. Daniel DeGray should have put his posts in here and here. So in a way, I feel justified in ignoring this one and ignoring this one. I'm not going to. I'm going to play nice. But the instructions from the outset were there are as many threads as there are problems. So that's kind of the first issue that I see here, is so that we don't just spray the thing out. Somebody kicks it off with problem 1, all the other problem 1 posts go into that thread, and same with problem 2. So I'm a little confused as to why that's not happening. I'm not sure how I can make it much clearer. If there are 2 problems, there should be 2 threads, not 4. So in the future, Daniel and Gary, put your responses to the problems in the proper forum. So if I look into Zach's here, pretty straightforward. So that is a problem. I mean, someone should have responded there. And let's just see where those ended up. So in the future, please put new posts for a problem forum into the proper. So let's just do it this way. Okay, so I'm going to have trouble with this complication thing. Everything we need for the assignments are in different locations in Moodle. Well, I'm not sure what he means by that.
Yeah, I mean, I think the guy who designed this course, is a little scattery, but
okay.
You made a point, I think, a couple weeks ago, I'm not sure that's not necessarily a bad thing, because it makes you kind of have to suss out information that's not just clearly apparent.
Yeah, I mean, this course does, am I recording this thing? Yeah, this course does force the student to feel a little bit of the pain of the engineer. I'm sorry, but that's the way it is. This is not just, hey, here's a word problem, go solve it course. It's just not. Because these regulations change, and yeah, it does. The point here is you're in the 4th semester of the program, and you're about to go out into the real world, so there's a little bit of a taste for it, and when I click on the link instead of, so in terms of that, I think what you can do, if you do a control click, so here's my answer to that, Gary. If you go anywhere on a link, and if you want it to come up in a new tab, the thing to do is control click, and that'll bring up a fresh tab. So for example, I just did that right here. So I did control click on Forum 6.
And you know, I think you may have an Apple which might have different.
Oh, yeah, it might be different on the Apple. Okay.
It'd probably be worth just going and checking, Google, like how can I open a link in a new tab with iOS.
Right. Okay, and then let's just take a look at this one too. So again, okay. All right. Well, we've seen the solution, so I am just going to move on to week 7, because that's where we are. Week 7. Capacity factor and design side management. All right. So one thing that's kind of cool and special about electricity is traveling at the speed of light, and therefore you use it as soon as it's created. It's just, of course you can store it, but unfortunately right now in Montana we have virtually no storage to speak of, the Gordon Butte pumped hydro being the one example that's about to change all that. Okay. So I'm just going to read through this. I'm not going to read it out loud. Okay. Yeah, this is pretty key or pretty critical, and I had the distinct honor and pleasure of visiting the main control room for Northwestern Energy there in Butte. Was it Butte? Yeah, it was Butte. Last year, yeah, it was about a year ago. We had a group out of Korea come through, and there were three people. They all just so happened to be men, but there were three men sitting there running Northwestern Energy. Each of them had about 20 monitors in front of them, so 60 computer monitors total, and that thing has to be staffed 24/7, 365. But one of the graphs that was sort of the most intriguing to me was this, where you basically had amplitude and frequency. And so by amplitude, what I mean by that, our grid runs on AC. So this is amplitude, and this is frequency. And in a sense, one way to think about this, and it's really almost identical if you think back to PV and how photons work. So a photon that does this has a high energy, and a photon that's doing this has a low energy. So in the case of light, E equals H nu. H is Planck's constant, nu is frequency. So the higher the frequency, the more energy. Now, it's true here. The faster you wiggle that signal, the more power you have. So more or less the way to think about power is, and this is just, I'll write it like this, but power, I'm just going to say, is proportional to amplitude times frequency. That's just like a way to think about it. Yeah? Oh. The power engineer just left the building. But the analogy I'm making here is that when load exceeds generation, the frequency drops. Okay, so what happens is the grid's coming along, doing its thing, just buzzing along. All of a sudden, this and let's just say this is the load. So here's the production, and here's the load. And both of these are a function of time. If the load is steady, we're going to have that steady frequency that I just drew. Now, all of a sudden, the load goes up, and this is an exaggeration, the frequency is going to go down. You're sucking power out of the system. That's the visual on what's written on the website here. Okay. And the point I was going to make earlier about Northwestern Energy is there's a giant bullseye, and they have to keep the grid in that bullseye. Sometimes it's here, sometimes it's here. It's just kind of walking around, but that is the target that the engineers are trying to hit all the time. If the amplitude goes high, you start to blow circuits. If it gets out of phase, well, the best way, and I'll just have to do some hand puppets, but in terms of the phase, it's a little bit like, jumping rope. Here comes the rope, I better jump every time the rope comes around. If all of a sudden, hey, here comes like a double Dutch, ooh, that's a lot different. And if somehow those ropes collide, the thing crashes. Because literally in an AC system, you literally are just sloshing electrons back and forth. They're moving, but they're just sloshing. Sometimes they're moving left, sometimes they're moving right, or back and forth, whatever So it's critical that those electrons all be sloshing at the same rate. Just like if you were playing tug of war, heave ho, heave ho. You want everybody pulling in sync to maximize the power. Otherwise, if I had two AC signals, 180 degrees out of phase, boom, they cancel each other out. You don't have any electricity anymore. So that's the best way to think about it. Okay. And that's really why this course is so critical. Wind and solar can crop up some regularity, but not the greatest amount of predictability. So what we're saying is grid operators looking for more tools to balance load and generation. There was even a thing on the radio this morning, NPR was talking about smart metering in California, and people get points on a new phone on their app, and I guess it's got, and I wish I could remember the name of it, but there's 100,000 users out there right now that say, hey, I am going to cook my food or wash my clothes or do whatever at a different time of day so that I'm not making those peaking plants turn on and off. So Yeah, so that's coming. I mean, I shouldn't say it's coming, it's been here. We don't have to worry about it so much in Montana yet. Okay, so demand response is what I was just mentioning, so, and smart meters as well. Yeah. And so, and here's the collision between energy and money. If you want to use electricity when everybody else is using it, it's going to cost you more, just like any classic economics problem, supply and demand. Oh, and there we go, yeah. So this is not the easiest graph to digest, but what's being plotted here is exactly what I was trying to depict here. So in this case, I'm going to call this 60 hertz, and I'm going to call this guy, and I'm just going to I'm going to call it 60.01. So this is going to be 60.01. So it's 1/100th of a hertz different, and I'm going to call this 59.99. So that's what we're looking at on this graph. So it's frequency as a function of time. So if everything were hunky-dory perfect, that 60 hertz would just sort of sit there, and this dot would never ever move. But as I said, when the demand goes up, the frequency goes down, and when the lights come off, the frequency goes back up. And it's critical to maintain that frequency. Kind of like a heartbeat. You don't want the flutter, you don't want the arrhythmia, you don't want the, was it tachycardia and bradycardia? So it's the heartbeat of the grid. Okay. So thermal batteries, and sorry, but go to resources 7, that's where it is. It's not just right here, but it's in the middle shell. And so the domestic water heater it's a dump load. You're not going to take the heat from your water heater and turn it back into electricity, but the point is I'm willing to allow my hot water heater to just sort of sit at a low state for a certain amount of time. Okay, here comes a power surge. Let's pump some of that extra energy into my heater. I've also proposed that we do something similar with hydrogen as a storage media. So, for example, we've got this 50 kilowatt hydrogen electrolyzer, and what I think the best use of it would be to sit at the base of some, wind turbine. And I know for a fact that there are many times throughout the year, and I've had this conversation with Ryan Carson, one of our alums who works up at Judith Gap. He'll say, yeah, there are a lot of times where we're just making too much electricity, and there's just not enough demand. Mm-hmm. And so where would you put it? Well, make some hot water, make some hydrogen, charge a battery, blow up a tire, do something with it rather than just furl the wind turbines or send it somewhere else. Unuseful.
Is there one storage medium that's just obviously more efficient than another?
It's tough to beat pumped hydro. It really is. The generators for hydroelectricity are well above 90%. And I think the pumps aren't that far off either. So yeah, you lose a lot less. You lose a little bit to viscosity, a little bit to pipe friction, a little bit to acoustics, but the motors are quite efficient. So, whereas if you're dealing with batteries or hydrogen, you're sort of going through some chemical losses, and there's usually more heat involved there. Yeah. and I'll let you dig through this. Cost of coal, shortcut factors, kilowatts to coal. Okay, problem number 1. So again, these are problems that are, real life problems that Alan Fraser has encountered in his own professional engineering experience. So, Electric Power Research Institute, he spoke with a member of SMUD, Sacramento Municipality District, using compressed air. Okay, so SMUD owns a wind farm with an underground cavern, and they own the mineral rights, so they own the cavern. Now, as we'll see, compressed air is not the most efficient, but it's there. Just pump some air underground. Since the profile is mostly at night, so the wind's blowing at night, it seems like a good match to store it while prices are low and sell it during the day when they're high. Okay, so the cost of energy during non-peaking hours is $20 per megawatt hour, or 20 cents per kilowatt hour. Relatively expensive by Montana standards, but these are not out of the question costs. Cost of energy during peak, $50 per megawatt hour, or 50 cents a kilowatt hour. So this also gets back into the whole net metering issue, and how, and right now, the push from the state legislation is to actually treat residential owners like primary power producers, which, there's arguments for and against. The wind farm is capable of making 100 megawatts. That's at full tilt. The capacity factor is 27%. It's not running at 100 megawatts 24/7. It's running an average of 27 megawatts. Sometimes it's 100, sometimes it's 0, but on average it's 27. That's what the capacity factor is. Okay, 70% of it is produced during non-peak hours, so which is kind of bad news, because you'd like to be making electricity while people demand it, but only 30% of your energy is made while demand. The other 70 is when the lights are off and people are sleeping. Okay. What's the revenue for peak, non-peak, and both together? So, pretty simple, straightforward. So compare base case to energy storage option. Okay, so if that 70% could be stored and sold, how well could you do? So just take that 70% that's running during this off-peak, store it, knowing that you're going to lose 50%. So that was kind of part of the problem doing the belt and the motor and the fan and everything. You're going to have some system losses, and you're going to lose about half of it. Now, this says for extra credit, make a table or a graph of this problem using these variables. Different on-peak or off-peak percentages, so tweak the 70, and you could run that from just, once you've done it for 70, 0, 10, 20, 30, you could run it for 11 scenarios. So that's kind of also the magic of Excel or any other computer code. Once you've solved the problem once, you've solved it as many times as you care to keep solving it. So, yeah. And then you can also tweak this variable. So all of a sudden, this problem, which is just a point in space and time, becomes a multi-dimensional problem. It allows you to run the slider, run this slider bar, run this slider bar, run this slider bar, and run this one. So you basically have 4 separate variables to tweak, and all of a sudden you've got a 4-dimensional matrix to look at. I'll just give you an example. So, so we could say we're looking at so we could do it once for 70%. We could do a 70% table, and then we could have a few different values for this. So this would be $20, $30, $40, and down here, actually let's take this X, Control V, and here it would be 50, 60, 70, and then you'd have basically 9 values, and you're just running at 70%. So once you've done that, you can take that and say, well, let's take it over here, copy, paste, and run that at 80%, for example.